Hi, and welcome to this video on hypothesis testing from the Year 2 section of the Stats course. And in this one we're going to be doing our hypothesis testing with the pmcc, the product moment correlation coefficient. So we're looking at hypothesis testing with correlation. This is essentially what's going on here. So when we plot data values on a scatter graph and start trying to calculate pmcc and lines of best fit and all that kind of stuff, generally speaking, what we're doing is taking data from an experiment, or we're only taking certain data or a sample of data from a larger population. So if we have a look at a data set in this diagram here, what we've got is quite a small number of points, and we've got a value of R, our PMCC, which is 0.909. So we're quite rightly saying, okay, this particular set of data here has got a strong positive correlation. But then we remember that it's actually coming from a much larger population potentially. So let's now imagine we can overlay that larger population, take all our data and plot that, and we find it's looking like that. So we can see the blue values here are the ones that we plotted originally, with the value of R is 0.909. But when we look at this now, this is looking less like a strong positive correlation. So the question is, can we use what we see from our sample to make a judgment about our whole population set? So as it turns out, the sample correlation coefficient, R, can be used as an estimator for the population correlation coefficient, which is this Greek symbol here, which looks like a P, but bizarrely is pronounced rho. And so what we're going to do is we can use this idea to do a hypothesis test to determine whether the value of R for a sample indicates whether the population as a whole has a linear relationship. Now, there's a whole world of stats going on behind this that you don't need to worry about. It kind of gets slightly complex, but essentially what you're going to be looking at is, as long as you understand how to do the test and interpret it, then that is more than good enough. So that's what we're going to go through now. So what we're going to do is we want to test to see if rho is greater than 0 or less than 0. And if we're doing that, we're saying it's greater than 0, positive correlation, less than 0, then that negative correlation, so that would be a one-tail test. So we've got either our null hypothesis, which is rho equals 0, in which case there's no correlation, or H1, rho is greater than 0, in which case the correlation for our whole population is a positive correlation. Alternatively, that would be the equivalent for a negative correlation. So all we're really doing is we want to say, is rho greater than 0 or is rho less than 0? Alternatively, our two-tailed test would be to test if rho is not equal to 0. So there we go, our null hypothesis rho is 0, i.e. there's no correlation, or H1 would be it's not equal to 0, so there is a correlation. And what we've got to do is check our value that we're going to get from our PMCC against a table of critical values for a given significance level. All right, and all those tables have been pre-calculated. They're not on your calculator, you have to look them up, but you do get them in your formula booklet. And they look like this. So what you've got essentially is your levels of significance across the top here, and we've got them against different sample sizes here. In this course, you're looking at product moment correlation coefficient. You don't need to worry about Spearman's, a slightly different thing. That comes up in the further math, so you're just looking at this table, part of the table on the left here. Now, as with all maths, it makes a lot more sense if we have a look at an actual example, and then we can see what's going on. So, first of all, we've got a series of data that's about test scores from students in maths and science, and we're going to calculate the value of R, the PMCC, for this particular sample, and that's a straightforward job. It's a case of taking all the values from the table, banging them into the calculator, and checking out the value, and the value of R we get from this data is 0.5897. So it appears that for this data sample, what we've got is a positive correlation. But the question is it a strong enough positive correlation in order to say that, okay, this would work for all test scores for students in maths and science? So what we're going to do now is set up a hypothesis test based on that. Our hypothesis test is looking at whether or not results show evidence of positive correlation. Tripping over my teeth, do apologise. Positive correlation. So here we go. So, test for evidence for positive correlation, and since we're specifically looking at positive correlation, we are looking at a one-tailed test. So let's set this up. There we go. H0, rho equals 0, or H1, we've got a positive correlation, rho is greater than 0. What we're going to do now is pull up my table of values. What we've got to do is work out our sample size. Let's just have a look at how big we've got here. We've got a sample of 10 data values, and we're looking at the 5% level. So there's our 5% level. There's our sample size, so that's the figure that we are looking at, 0.5494. So that's our critical value. And what we've got to do is compare the critical value we've got here with our value for R that we've got here. And because it's greater than 0.5494, our observed value of R is in the critical region. And if it's in the critical region, what that means is that we're going to accept H1. So there is sufficient evidence to reject H0 and accept H1, which means there's a positive correlation between test scores in maths and science at a 5% level. If this value had been less than 0.5494, then this would not have been a strong enough correlation, and so therefore not a critical region, and so therefore we would have rejected H1 and accepted H0. But in this particular case, because our value is bigger than our critical value, we're going to say yes, we have got a positive correlation. And the same thing would happen if it was a negative correlation, but then we would need a value that's kind of essentially close to the -1 would be in the critical region. And so it applies in exactly the same way, but just with negatives. And there you go.